Hello, good morning or evening or afternoon, everyone, depending on where you are attending from. My name is Albert Cohen, and it's a great pleasure to chair this seventh and last online seminar organized by FoCM. So today we will have two seminars, one by Rekha Thomas and one by Danylo Radchenko. As usual, you will be allowed to ask questions in the end of the talk by raising hand, and then we let you open your mic. And after the second seminar, everyone can stay and socialize a bit more. So let me introduce our first speaker, Rekha Thomas. Rekha did her PhD in the field of operation research in 1994 in Cornell University, directed by Bernd Sturmfeld. She held a permanent position at Texas A&M, and since 2000, she is a professor of mathematics at the University of Washington. Rekha's research are famous in optimization theory, applied algebraic geometry, and in 2013 she became one of the inaugural fellows of the AMS, the American Mathematical Society, and it's a great pleasure to listen to her today. Her lecture will be about chirality in vision. Rekha, the floor is yours.
Thank you, Albert. Let me just share my screen first. Okay. Thank you, everyone, and thank you for coming, and thank you for inviting me to this series. So I would like to tell you about a topic that I'm calling chirality in vision. And this is a question about, it's a very basic geometric question that arises in the area of computer vision, more specifically in the area of reconstructing three-dimensional scenes from images in cameras. Okay. So when we say reconstructing a scene, it really means, or reconstructing images, it really means we have some potential images that were taken by cameras, and we would like to reconstruct both the cameras that took those pictures as well as the three-dimensional scene that actually imaged in those cameras to give you the image that you have in front of you. Okay, so that is what reconstruction involves. And a very basic necessity for reconstruction, if you think about it, is that the three-dimensional scene that you reconstruct really has to be in front of the cameras, right? It has to be visible to the cameras. And this just seems completely obvious, but in a lot of models that treat image formation and reconstruction, this semi-algebraic condition of being in front of cameras is usually ignored. Okay, so usually image formation is modeled algebraically, and this sign condition that is required, which is what chirality is about, is ignored. So what I want to talk about today is what happens if you bring chirality into the picture, and what sorts of results do you get. It's definitely far more complicated than just looking at the algebraic model of the problem. And I would like to show you some of the results that are possible. Okay, so that's what this talk is about. Chirality has been studied in vision by researchers in vision, primarily initiated by Richard Hartley back in the late 1990s, and several other people have worked on it too. I don't have a ton of references in this talk, but if you look at the papers, then everything should be available to you. Okay, so this is what the talk is about. And let me say first off that this is joint work with several people. So on the extreme left is Samir Agarwal, who's been a long-term collaborator of me. He works at Google here in Seattle. And then Andrew Pryhuber, who was a joint student of Samir and mine at the University of Washington. He just finished his PhD in math and currently works at NVIDIA. And Rainer Zinn, who is a professor at the University of Leipzig. Okay, so let me start by posing the main question that I would like to talk about in this talk. Okay, so suppose we have the following situation. We're given K point pairs, let's call them UI and VI, that live in R2 cross R2. The question I want to ask is, when are they images of K points in the world, which are called world points usually? So when are they images of K world points in two cameras? Okay, so this is a question I will talk about throughout today. So let me pause a little bit about the question itself. So these two rectangles that you see here are supposed to represent two camera planes. And I'm given paired points. I'm given a U1 in the first plane and a V1 in the second plane. They're linked in the sense that they're both supposed to be images of a single unknown world point, which maybe we will call Q1, okay? Similarly, U2 and V2 are paired, U3 and V3 are paired, U4, V4 are paired, and in general, there are K such point pairs. And the question is, is this really the picture of K points in the world under two cameras? So here I only have two cameras, but you could ask this question for any number of cameras and any set of, linked points like this in the several images. But you'll see that the two camera question is already pretty complicated and rich. And I will give you an answer to this question. Okay, so this is the question we want to ask. It's very basic, very old question in some sense, and so this is what we're going to talk about today. Okay, so can you reconstruct these point pairs in the sense of finding two cameras and finding K world points that image to them? Okay, so to talk about this question, we first need to fix the model of a camera, right? So there are many models of cameras. Cameras can have very complicated nonlinear models, but for today, I will just stick to the classical pinhole camera, or more generally, something that I will call a projective camera, okay? So what's a pinhole camera, right? So pinhole camera has two components. It has a viewing plane, which is this blue plane that you see here. So that is the camera plane, and it has a center, which I have placed at the origin of the world coordinate frame, okay? This perpendicular line that emits from the center to the plane and goes outwards, that's called the principal axis of the camera. And this point here, this P point where the principal axis intersects the plane, is called the principal point of the camera. Okay, so how does a camera take a picture? So if I have a point Q in the world, then what you do is you draw the line segment that joins Q to the center. And wherever that line segment intersects the image plane, U, that is the image of Q in the camera, okay? So if we make a cross-section of this picture that you see on the left, you get this picture on the right. And then if you do a little bit of simple, similar triangle geometry, you can actually calculate the coordinates of U. So what this gives us is a map from R3 to R2, R3 where the world point lives, which is Q, and R2 which is the image plane of the camera. So what happens is Q1, Q2, Q3, which is our Q point, maps to F Q1 over Q3 times F Q2 over Q3, where F is this distance from the center to the camera plane. Okay, so this is the focal length of the camera. This is F, and this is the formula. Okay, so we have a formula for this point U. Of course, the point U has Z coordinate fixed, so we just drop the Z coordinate and we just write it as Q1, Q2, Q3 goes to this rational image, okay? Now, this is fine. There's no problem with this, except that rational maps are not that great. So the typical trick in computer vision is to bump everything up into projective space and convert this map into a linear map, okay? So the way they do that is you turn R3 into P3 by adjoining a 1 at the bottom of the Q1, Q2, Q3. And similarly, you adjoin a 1 at the end of the image. And so now we have a map from P3 to P2. And this is exactly the same as what we had before. But because we are in projective space, I can now scale things. So this point over here, I can scale by Q3, get rid of the denominator. And then you will see that that point will be just exactly the product of this matrix, this 3x4 matrix here, times the world point, which is Q1, Q2, Q3, 1. Okay. So this 3x4 matrix, which has rank 3, this is the camera matrix. And now we have a linear map from P3 to P2, and this is what a pinhole camera is in Vision. Okay. So this is the model that we will use. These pictures, by the way, are from the book of Hartley and Scissorman, which is kind of the Bible in multiview geometry, which is the geometric, which deals with a lot of geometric aspects of computer vision. Right, so that's a pinhole camera. So we can generalize it a little bit. We can, in general, define what's called a general projective camera. And this is simply a map from P3 to P2. It's a rational map that takes Q, which is a point in P3, which is called the world point, to A times Q, where A is a 3x4 matrix of rank 3. Okay, so this is what a camera is, a 3x4 matrix of rank 3 for the rest of the stock. Okay, we really want rank 3 because otherwise the world will just collapse onto a line or to a point, which we don't want. We really want the map to go from P3 to P2. We want a two-dimensional image. Okay, so because my matrix is rank 3 and 3x4, it has a unique right kernel in projective space. And that point is the center of the camera. So the center of the camera is the C in P3 such that AC is equal to 0. So in projective space, it's a unique point. In affine space, there's a whole line. Okay, here's another little bit of terminology. So if I partition my matrix into the first 3x3 block and then a column, let's call that first 3x3 block G, then you call the camera finite if the determinant of G is not 0. So the first 3x3 block is invertible, in which case you can calculate what C is. So C just becomes this formula over here. And you notice that C is actually a finite point in projective space. So the camera is finite exactly when the center is finite and vice versa. Okay, so that's another piece of terminology. And with this, we can formally describe what we mean by a projective reconstruction. Okay, so suppose I go back to my point pairs that I had before, K of them, UI, VI, then a projective reconstruction of these point pairs means finding projective cameras, A1 and A2, so two 3x4 matrices of rank 3. You can assume they're finite, and world points, Q1 through QK in P3, such that when you do A1 QI, so you image the ith world point in camera 1, you get exactly the point UI, but now everything is in projective space, so a 1 is attached at the bottom. So the squiggle here just means they're equal in projective space. Okay, so we want A1 QI to be UI1, and we want A2 QI to be VI1. And we want this for every I from 1 through K. Okay, so this is a projective reconstruction. And as you see, this is just algebraic, right? We're just requiring that A1 QI is UI1 and A2 QI is VI1. So this is the algebraic model of image formation in pinhole cameras. Okay, so this is what a projective reconstruction is. Okay, so these questions, the question that I'm asking about reconstruction is actually really, really old. Okay, so these questions were asked a long time ago because projective geometry has been around a long time ago. So here, for example, is a question that was asked by the French mathematician Charles in 1855. He asked the following question. So if you're given UI, VI, 7 of them, 7 point pairs, and you know they're images of Q1 through Q7 in 2 projective cameras, show that there exists at most 3 projective reconstructions up to P3 automorphisms. This was a question asked by Charles, was answered by Hesse in 1863. Okay, so old question. And one reason why these questions were so popular, even as long ago as in the 1800s, is because of photogrammetry. So photogrammetry preceded photography, and people really were interested in understanding how to reconstruct 3-dimensional objects from pictures or maps, for example, in archaeology, or in creating topographical maps and so on. Okay, so these questions are very old. And the question that I'm asking, which I showed you on the first slide, sounds really basic and simple, but the answer was not really completely known. Okay, so this is a type of, this is not our question, the one that's on the slide, but I just wanted to show you a historical slide just so you see the similarity of the question. Okay, so now let me introduce what chirality means. So we already saw what a projective reconstruction is. And as I said in the beginning of the talk, it's important that the points that you reconstruct are in front of the camera. Okay, so what does that mean? So let me recall what the principal ray was. So remember, the camera has this perpendicular that comes from the center through the camera plane and goes outward. This is the principal ray. And let's suppose that the direction of that ray is n sub a. Okay. So if your point is in front of the camera like this, then, so first of all, the direction of the principal ray denotes the front of the camera. Notice that if the point is actually in front of the camera, then the projection of this line segment from the center to Q onto the principal ray will be a positive number. Okay, so that, the length of the projection will be positive. So this length is called the depth of the point in Q. Okay, and this depth is simply the projection of the line segment from C to Q onto the principal plane. And so if the point is in front of the camera, this projection is some positive amount, or the length is positive, and we are going to call chirality of Q and A the sign of this depth. Okay, so the depth is positive if and only if the point is in in front of the camera, and we only care about whether it's positive or negative. So we only care about the sign. So that I'm going to call the chirality of Q in A. Okay, so the point Q is now in front of the camera if and only if the chirality is 1. So chirality can be either 1 or -1 if we start with a finite point. I'm going to declare that the point is in front of the camera if chirality is 1, or equivalently, depth is positive. Okay, so now we're ready to define what it means to have a chiral reconstruction. So chiral reconstruction of my original point pairs, K of them, means I first off need a projective reconstruction. So I need 2 cameras and I need world points that image in those cameras to my points. But in addition, I want all the world points to be in front of the 2 cameras. Okay, so what this exactly is a little bit complicated. Okay, so if there's only 1 camera, it's just saying that the depth is positive or chirality is 1. And it's fairly easy to figure out what happens to the plane at infinity, for instance, what happens to infinite points, which is not actually captured by depth. But when we have multiple cameras, this notion of what it means to be in front is a little bit sophisticated. So let me try to explain what that is. Okay, but the main point here is that chiral reconstruction requires projective reconstruction plus this additional requirement that the points that you reconstruct, the world points, have to be in front of the 2 cameras. So here's a picture of a projective reconstruction that is not chiral, just to give you an idea of what the distinction is between the 2 reconstructions, right? Again, this is from the book of Hartley and Sisselman. So here's a comb, and then on the other side, you see a projective reconstruction. So it satisfies all the algebraic equations, but it's not chiral. Okay, so this reconstruction splits across the plane at infinity, and therefore you see this very funny picture of the comb. So this is not what we want. This is what's typically done even in practice today, both theory and practice. People look for projective reconstructions, and because everything is done on large data sets, statistically, you throw out the things that don't make sense. That's basically how things go. Typically, but we would now like to disallow reconstructions that look like this. Okay, so now I can tell you a little bit more about how we approach chiral reconstructions. All right, so the very first thing to define is what I'm going to call the chiral domain of a camera arrangement. Okay, so suppose I have M cameras, and I'm calling this script A. So script A is this tuple of M cameras. They're all projective cameras. And I'm going to define what's called the chiral domain of this arrangement to be the closure of all the finite points Q that have positive depth in every single camera in my arrangement, okay? So if you're a finite point, there's no problem. You just check chirality in every single camera. It has to be 1 to be declared to be in this chiral domain. But the interesting part is in this closure, okay? So when you take the closure of this set, you actually pull in points from infinity, from the plane at infinity, as well as from the principal plane, which is the perpendicular to the, which is the perp of the principal ray, okay? So those are the interesting points that actually get pulled in, and you'll see that it's actually a little bit interesting. So we're going to declare a general point Q in P3, not necessarily a finite point, but any point Q in P3 to have chirality 1 if the point Q lies in this chiral domain. Okay, so chiral domain is basically everything that is visible to my cameras. That's basically what I want it to be. And I'm defining it to be the closure of all finite points that have positive depth in every single camera. Okay, so let me show you 2 pictures just to give you a sense of what this means. So on the left here, you see 2 cameras that are facing in the same direction. Okay, so their principal rays are the same, but their principal planes, which are the perps to the principal rays, they are parallel but distinct. Okay. So in this case, we expect that the plane at infinity is visible to both cameras, right? Because you can see that as you approach infinity, there are points with positive chirality, with chirality 1, sequences of points that will approach there. Whereas in this picture, what we expect is that the cameras are facing each other. So it should not be that both cameras can see the whole plane at infinity. So it turns out, it looks from this picture that the plane at infinity will completely disappear. But some parts of the plane at infinity can still be visible because all this is happening in higher dimensional space. So this is just to give you an idea. But so to work with this definition, which is not very convenient, we are going to first translate this or give it a semi-algebraic description, okay? So here's the first theorem that we proved. So we defined the chiral domain, and then we proved that this chiral domain can be just given, can be written as a semi-algebraic set that's given by certain quadratic inequalities. So what are these inequalities? So n infinity is just the normal of the plane at infinity. So this is just 0, 0, 0, 1, okay? And ni, I'm going to call the principal ray of camera I. Okay, so that's also fine. And then with those 2 definitions, we can define the chiral domain to be all the Q in P3, such that for every pair I and j, I have these inequalities. So the first inequality is that n infinity transpose Q times nj transpose Q is non-negative. And then similarly, I have inequality for pairs of cameras. Okay, so these are certain dot products, and we're just requiring that they are non-negative, which means that either the 2 dot products are both positive or they're both negative, or one of them is 0. Okay, so these are the inequalities. And for example, in my first example that I showed you on the previous slide, I talked about how the plane at infinity should be visible in both cameras. And indeed, if you look at what this region is, which is shown here in yellow, you see that the plane at infinity, which is this vertical line, is entirely inside the chiral domain. Okay. And in the second case, from this picture, it looks like the plane at infinity. This is the plane at infinity now, this horizontal one. It looks like only 1 point is visible, but in fact, there's actually a whole line visible, which because this picture really is living in R4 or P3, wherever you want to work with. And I've drawn the picture in 2-dimensional space. Okay, so it's not so important if the details are not so clear, but the key point is that there is a semi-algebraic description of this chiral domain. And this description, even though it looks quadratic, it's actually cutting out a polyhedral region, as you see in these pictures. Okay, so they are like cone conditions, and it's just what you see in these pictures. So now we have the chiral domain. So this is the part of P3 that a set of cameras can see. And as hopefully I've given you, as I've tried to explain, that this definition is a little subtle when you have many cameras. If you have one camera, everything is okay. But if you have more than one camera, you have to be careful what gets pulled into the closure. Okay, so now let me come back to the question. So our question is, again, we have these K points, K point pairs, UI, VI. And now I'm going to just assume they've already been homogenized. So they have last coordinate 1. So let's put them in P2 cross P2. They are real points. And projective reconstruction of the points means finding 2 cameras, A1, A2, finding world points, Q1 through QK, such that these algebraic conditions are true. And chiral reconstruction means we, in addition, need all these semi-algebraic conditions to be true. Okay, so this is the type of reconstruction I'm looking for. So cameras, world points, algebraic conditions are true, and semi-algebraic conditions are true. Okay, so we want all of this to happen. So the question we were asking in the beginning is, when is it possible that if you give me point pairs, they will have a chiral reconstruction? Good, so that's the question. So now I'm ready to give you the answers. So we can actually completely answer this question, and here's how the answer looks. So the first piece of the answer is that if K is less or equal to 3, so if you arbitrarily give me 3 points on one side and 3 points on the other side, then there's always a chiral reconstruction. It doesn't matter what geometry the 2 points have, 2 sets of points have. Okay, so they could be non-generic on one side, generic on the other side, doesn't matter. They will always unconditionally have a chiral reconstruction. Okay, this is the first result. This is not that hard to prove, but it's a good starting point for where we can think about these results. So this is the first result. So this is in a second paper we wrote with Pryhuber, Sin, and myself. And the next result is that if you have 5 or more points, okay, so 3 was completely okay, but now let's jump to 5 for a moment. So if you have 5 or more points, then the configuration may fail to have a chiral reconstruction with positive probability. Okay, so what does that mean? So let me explain this result a little bit. So first of all, examples of 5-point configurations that do not have a chiral reconstruction were constructed by Thomas Werner back in 2003. So he gave some examples. And this example that I'm showing you down here is a modification of one of his examples. So let's assume that this is the image that you see in one camera, and the green ones are the images you see in the second camera. Okay, so if I start with the blue image on the left in camera 1 and green image on the right in camera 2, then there is a chiral reconstruction. But if I change this green configuration to what you see down below, which is the only change is in the 0.5. So the 0.5 went from this corner in the bottom here to up here. Okay, that's the only change. If you do that, then suddenly there is no chiral reconstruction. And this is, as I said, is a modification of an example of Werner. So this just is to illustrate that you can have these 2 situations. Now, the more interesting fact is that you see this configuration down here that doesn't have a chiral reconstruction is actually in general position. No 3 points are in a line. And if you wiggle these points slightly, they will continue to not have a chiral reconstruction. Okay, so this is what I mean by the P can fail to have a chiral reconstruction with positive probability. So the set of point pairs, 5-point pairs, that fail to have a chiral reconstruction is actually Zariski dense. Okay, it's not a low dimensional space or anything like that. It's actually Zariski dense. So this is the other side. So 5 points and above is going to be bad because 5 points are already bad, and then you can always embed this into more number of points, and it'll continue to be bad. Okay, but of course some of them do have a chiral reconstruction. I'm just saying that there exist bad examples. So that leaves what happens with K equals 4. Okay, so that is the most interesting and the most complicated case. So in K equals 4, here's how the story will go. Okay, so first of all, there are 6 combinatorial types that we can look at, right? So you can have In one plane, the points are in general position. The other plane also, they are in general position. So these are just cartoons. So this is general position, general position. We can have general position, 3 points in a line, 3 in a line, 3 in a line, or 4 in a line, 4 in a line, and so on. Okay, so if you think of all the possibilities, there are 6 possibilities, and I've drawn them all here. And the result is that in all the possibilities, you see a check mark. You have unconditional chiral reconstruction. You can always chirally reconstruct. Whereas if your configuration happens to be in these 2 possibilities, then you can fail. You may or may not fail, okay, but you can fail. And that completes the story for k equals 4. So this is complete. This is not about, there's nothing generic or non, so on about this result. So it's a complete result that looks at everything, including non-generic point configurations. So mathematically, it's better to state this result like this way, I think, in the blue that you see down here. So what we actually proved is this, that if you take your points U and make them the columns of a matrix, let's call that this script U, and similarly, you take the points V and make them into the columns of a matrix, then there's a chiral reconstruction if the rank of the 2 matrices are the same. So basically that's saying that if the geometry is similar on both sides, there is a chiral reconstruction. And in this case, these 2 cases where you see a cross, the geometry is quite different, right? So here it's a full rank matrix and here it's not. Similarly, here it's a full rank matrix and here it's not. So in those cases, you can fail, all right? So that's the complete answer to the question I gave you. I explained at the beginning of the talk, and that completes the story of chiral reconstruction. Projective reconstruction was known before, mostly known, and it has a slightly different story. If you're given 2 point pairs, when is there a projective reconstruction? It is not very simple, but it has been done in the past. Okay. So this is the story for chiral reconstruction. So in the remaining time I have, I want to show you a little bit about how you model such problems, like what is the geometry behind this and what are the tools that go into it. There are no proofs, but I just want to show you the geometry, and then you will see that the k equals 5 case, which is this case, has this very surprising connection to the theory of cubic surfaces in algebraic geometry. Okay, so let me spend the rest of my time trying to explain how you think about this problem. Okay, so here is the 2-camera geometry again. Okay, so let's come back to 2 cameras, which is the only case that I'm looking at today. So let's assume we have this camera A1 in blue here with a center C1 and a camera A2 with a center C2. If I want to take a picture of a point Q, then in my first camera, I will draw this line segment and get U as the image. In the second camera, I will get V as the image. Okay. Now these cameras have a little bit extra structure. So for example, if I image the center C2 in camera A1, it'll image here to this point called E1, which is called the epipole of camera 1 with respect to camera 2. And similarly, if I image the center of the first camera in the second camera, I will get this point, which is another epipole. So these 2 points are special. They're called epipoles of the camera pair. And the line that joins the 2 centers is called the baseline of the cameras. Okay, so that's some terminology we will need in a moment. But the key thing that this picture is showing us is that if I take a picture of Q in 2 cameras, U and V, and suppose I tell you where U is, then the position of V is not arbitrary, right? So the position of V is determined by the fact that the Q, the center C1 and the center C2 all lie in a plane. So they lie in a plane. So if I give you U and the 2 centers and my world point, then I know uniquely where this V is going to be. Okay, so that's a planarity condition that links the Q, the centers, and the 2 images. And that planarity condition can be translated into algebra. And it's just saying that there is a rank 2 matrix X that is 3 by 3. It's only defined up to scale. So it's actually in projective space, but it's a real matrix of rank 2, such that if you multiply V transpose on the left and U on the right, you will get 0. Okay, so U and V are known. So this is just a linear equation in the entries of X. Okay, so this planarity condition is can be translated into this algebraic condition, and this X is called the fundamental matrix of the two cameras. Okay, the two cameras with respect to these 2 points U and V. Okay, so we're going to work with this fundamental matrix X. And it turns out that if you know the fundamental matrix, you know the cameras. And if you know the cameras, you know the fundamental matrix. So reconstructing the cameras is the same as reconstructing the fundamental matrix. So this is a very handy thing. So now we really have 3 different frameworks in which we can think about reconstruction. So the first framework is what I explained at the beginning of the talk. Reconstructing means finding cameras and world points. So this is the first framework. You can work in the space of cameras and world points and try to find cameras and world points that reconstruct your images. The other possibility is we can work in the space of fundamental matrices. So remember, that's the same as finding cameras. So I could look for X's that live in P3×3, real X's, rank 2, such that they satisfy all these linear equations. Now I have K linear equations because I have K point pairs. So these are called the epipolar equations in computer vision. Okay, so we could work here. 3×3 matrices have 9 entries, but I only care about the matrix up to scale. So really we're working in P8. Okay, so this is one other space you could work in. Now, if you have a rank 2 matrix that's 3×3, it has a unique right kernel and a left kernel in projective space. So we could also just work in the space of the kernels. Okay, so we could look at this E1 and E2 such that E1 is the right kernel and E2 is the left kernel. So that also is fine because from there we can reconstruct X, and that is in P2×P2. Okay, so we have 3 different places where we can do this reconstruction. And it turns out that this right kernel and left kernel of X are in fact just the epipoles. So we often call this the epipole space. This is the fundamental matrix space, and this is the camera space. So to solve these problems, we mostly worked in the fundamental matrix space and also in the epipole space, and did not work in the camera space. Okay, so which was how I phrased the question in the beginning, but it's more convenient to work in these other projective spaces. Okay, so now let's impose chirality. So if you impose chirality, then in camera space, you needed to respect these principal rays, right? There are these directions given by principal rays, those Ni transpose Q and J transpose Q, those inequalities. That's what you get here. If you translate that into fundamental matrix space, then you also have to satisfy certain inequalities. These we call chiral inequalities. They are degree 6 polynomials. They're fairly complicated, but because they're even, they are fine to work in projective space, right? So whether I plug in X or minus X, the sign won't change. So the trick to work in projective space with inequalities is to make sure that the degree of the inequalities or the polynomials are even. So these are degree 6 polynomials. They're quite complicated. And then if you translate that into epipole space, the whole thing becomes an oriented matroid check. So you have to check signs of certain determinants. So this is how the chirality transfers into these 3 frameworks. All right. So let me just say now how we are going to pass to geometry. Okay. So let's look back at what it means to have a fundamental matrix. So fundamental matrix means 3×3 matrix of rank 2, also has to be real. Let's relax. Let's just say, okay, let's just look at 3×3 complex matrices of rank at most 2. Okay, so this is a relaxation, but it's a nice relaxation. Now we have an algebraic variety. So I have a complex variety, just a hypersurface in P8 of degree 3. Okay, so this is a relaxation of the first piece of the fundamental matrix requirement. The second piece here is just a plane, right? It's a codimension K plane because these are just linear equations. The UIs and VIs are known, X is unknown. So this is a codimension K plane in P8. So what fundamental matrix means is that I need to be in the intersection of this R2 variety, which is the rank at most 2 variety, and the plane. I need to be intersected by both. I need to be in the common intersection. That's what these conditions tell you. But these conditions tell you more. You also have to be in the real part, and you have to make sure the rank is 2 and so on. Let's ignore that part. Okay, let's ignore the complicated part, real part, rank 2 part for now. And I will just call this inside complex variety, I'm going to call it the epipolar variety of P. So it's very simple. It's just a determinantal surface, which is R2, cut by a linear space. Okay, that's what it is. So the linear space is codimension K. As K changes, the dimension of that space will change. So this is the epipolar variety of my configuration P that I had in the beginning. Okay, now on this variety, there are certain walls, okay? And these walls are given by our data. So the UI point gives you this particular wall, all the x's for which UI is in the right kernel. And I intersect it with my plane LP. And similarly for the VJ point, I look at all the x's that have VJ in the left kernel, and I intersect it with LP. Okay, so these are again subspaces because each one of these X thingies are subspaces, and I'm intersecting it with LP. So they are subspaces, they have a certain codimension. You'll see that they will turn out to be codimension 1 on this epipolar variety. That's why I'm calling them walls. And then if you intersect the ith wall and the jth wall, you will get, codimension will increase 1 more, and we will get something that I will call a corner. Okay. So the picture is like this. So let's suppose this is our epipolar variety. I have these walls on the epipolar variety given by the point configuration. This is a corner. This black dot is a corner. And the key property for us is that these complicated polynomials that are imposed by chirality, this degree 6 GI-GJ polynomials, while those polynomials are complicated, they will vanish exactly on these walls. Okay, so if we just care about sign change, we just need to understand these walls. Okay, and the chiral regions are going to be given by certain chambers that are cut out by these walls on the epipolar variety. So the epipolar variety is there. The walls are codimension 1 linear things on those on that variety. It cuts the whole variety into cells, and we're looking for certain cells that will satisfy the right sign conditions. So that's what the chiral regions are. Okay. So let me elaborate a little bit on in the case of this of k equals 5, which is the most interesting case. So in the case of k equals 5, what happens is generically, the epipolar variety is a smooth, irreducible cubic surface. So here's the famous picture of a cubic surface, the Clebsch surface. And this is how the epipolar variety looks. And these lines that you see here are going to play an important role. Okay. Now, cubic surfaces have been studied forever in mathematics. So back in the 1850s, Cayley and Salmon already figured out there are 27 complex lines on every smooth cubic surface. Sometimes these lines are real. Okay, so the real topologies or real smooth cubic surfaces, or these, when you have real lines, the topologies are known, and we will be in the case where all of these 27 lines are real. Okay, so there are several possibilities. You can have 27 real lines, or 15 real lines, or 7 or 3. Okay, these are the possibilities. And it turns out that the cubic surfaces that come from vision are always going to have 27 real lines on them. And what are they? Well, 10 of the real lines come from our data. They are these walls, the UI wall and the VJ wall. Okay, so that's 10 of them. There is a 6th pair of walls that's hiding in the first 10. And the way you get that is you take your 5-point pairs that you were given, you turn them into matrices by doing these outer products. You take V1 times U1 transpose. So remember, each UI and VI are 3-dimensional vectors. So when I do this outer product, I get a 3x3 matrix. So I take the 5 3x3 matrices I get, they're all rank 1. They span a plane, they span a 4-dimensional plane in projective space. And they will intersect the rank 1 variety, which is a degree 6 variety, in one additional point, right? 5 of the rank 1 points are here, and there's the 6th rank 1 point, which is hidden, which I'm going to call V0, U0. So you will get a new point of intersection, and that will decompose into 2 more points, which are U0 and V0, okay? So really the 5-point pairs that we had in the beginning carried with them a secret 6th point pair, and that is this U0, V0, okay? So let's get them. So together now I have 12 real lines, okay? So you take the walls of all of them, that's 12 real lines. It turns out these sets of 6 lines here and 6 lines here, they form something called a Schläfli double 6 on this cubic surface. So that means that this set of lines are mutually non-intersecting, so they are skew. This set of lines are also mutually non-intersecting. And the I wall here and the J wall here do not, the I wall here and the J wall here will intersect if and only if I is not J, okay? So there's a very specific intersection pattern, which is the definition of a Schläfli double 6. So Schläfli double 6 on the cubic surface means exactly a pair of 6 lines and 6 lines that have this intersection pattern. No intersection in this group, no intersection in this group, but the ith one here and the jth one here will intersect if and only if I is not J, okay? So that is a Schläfli double 6. So these vision problems create a cubic surface with right now 12 real lines that form a Schläfli double 6. And then it turns out there are 15 more real lines that come from tritangent planes that you can construct from the existing walls. So let me not explain that, but there are 15 more lines that arise and they're all real, okay? So this is very, very special. It's a very special cubic surface that comes up from vision from this particular question. And finally, we can actually see the regions that are sitting above, right? So what's happening is up here, I have this configuration of lines on the cubic surface. They are dividing the surface into certain cells and among them, some of these cells are chiral. So if your X lies in one of these chiral cells, we're good, okay? So let me finish by just showing you how to visualize those cells. So one way we can't really visualize in P3. So P3 is where the cubic surface lives. So one thing we can do is, because I have a rank 2 matrix, I can blow it down, okay? So that means that if I think of if I multiply X with the adjoint of X, I will get 0, right? Because the matrix is not invertible, it's only rank 2, it's a 3x3 matrix. So that means every column in the adjoint of X is actually in the right kernel, and every row in the adjoint of X from here is in the left kernel. So what I'm going to do is I'm going to take a matrix X and just map it to a row in the adjoint and a column in the adjoint. In fact, I do column on the left and row on the right, okay? So if you do that, we will now blow down into 2 copies of P2. We started in P3, which is where the 3x3 matrix lived. I'm just pushing that, I'm just mapping this matrix down into its right kernel and its left kernel. So I go into, I get a map into P2 cross P2. Now, if you do this, something very beautiful and classical happens. So on the one side, on the left, the U walls will map to points. Okay, you see the 6 points, the 6 U points here. And the V walls will map to conics. And these conics are very pretty. So what's going to happen is the jth conic is going to go through all the U points except UJ. Okay, so once you know the U points, you can draw the conics because you know that 5 points will give you a unique conic. So the U walls will go to points, V walls will go to conics on the left, and on the right, the V walls will go to points and the U walls will go to conics. Okay, so this is classical, this is known very well in the study of cubic surfaces. But now that means that the chambers upstairs that were bounded by walls are now bounded by conics, and you will see this picture. Okay, so this is the chiral regions. You can see the chiral regions blowing down from P3 into these 2 copies of P2. So these gray regions you see here, exactly where you will get chirality. So what has to happen is that the epipoles, the one epipole has to be in one gray region, and the second epipole has to be the other gray region for a chiral reconstruction to exist. And we also have a theorem that says you don't really need to describe all these regions. You can just check the 20 corners that you get by intersecting an I wall and a J wall. So it's enough to test the 20 IJ corners to find the chiral region. So you don't really need to mess with inequalities or semi-algebraic sets or check their feasibility or anything like that. You can just test this determinant condition on 20 points to determine whether there's a chiral reconstruction. Okay, so that's basically most of everything I wanted to say. There is more to this cubic surface story. You can connect it even further to classical results in algebraic geometry, but I won't talk about it. So let me stop here. And the two papers that I mentioned are the ones that are written here. We have two papers, both in the last year, roughly, where you can see more details or get all the references. And that's basically it. Thank you.
Thank you very much, Rekha, for this beautiful, I think very aesthetic also talk. And please, are there questions? Please raise hand if you have questions. We have time for that. Maybe, okay, I will start by asking a naive question. So in concrete application, image application, so image have pixel values, I mean light intensities. The light intensities at the point did not at all enter the picture in your discussion. I mean, there were only points not labeled with a certain light pixel value intensity. How does it actually connect with what you do? I mean, this is a vague question. But
right. So I'm not a total expert in the practical side. So that the practical side is very big. And typically what people do is reconstruct millions and millions of points together, right? So you may have, say, 1,000 pictures of the Eiffel Tower that some tourist took, and now you can reconstruct the Eiffel Tower. So the first and foremost thing to do is exactly what I showed you in the picture, which is to match points. So if I see a corner of the Eiffel Tower in picture 1, I need to know where that corner is in all the other 1,000 pictures that I have. Okay.
Yeah, but this is precisely, I mean, okay, yeah, go continue.
Right, so this is one pre-processing that has to be done, which I didn't talk about. I just started with that. So there are people who do that, and that's a very difficult combinatorial optimization problem in some sense. It's a matching problem, right? So you need to figure that out. So once that's given, so the reconstructions I'm talking about are simply reconstructing points, but you could reconstruct other things. You could reconstruct lines, you could reconstruct curves, you could do more complicated geometric reconstructions. The other point I wanted to mention is that in general, the points are noisy, right? So it's not an exact, so typically there is no exact reconstruction. So we would turn this into a statistical estimation problem. So it would really have to be minimized distance to some model, or find an MLE. That's what it is. So you don't ever get anything quite the real thing because your data is noisy already. And a third point is that the way people normally reconstruct is by something called random sampling consensus. So this means that you take 5 points, you reconstruct, get a fundamental matrix, then take another 5, and reconstruct, and then match it against the points that you did not deal with, and then pick the one that is the best. So there's all sorts of, what shall I say, like statistical methods, heuristical methods to actually reconstruct, and they're incredibly fast. They're very, very good. They have very sophisticated optimization algorithms behind them. The line of work we are doing is much more looking at the basic math behind these problems. So there's a wide gap between what is done in practice and what is done here. And we are not taking into account the pixel value or anything like that, right? These are just points that we are reconstructing. So I'm not sure, in fact, I don't know in reality how people think about things like pixel values.
Yeah.
But this is a much more basic question.
Yeah, okay. So other questions or comments? If not, I could have another one, if I may, which is this. This is an inverse problem, basically, where you try to recover some 3D object from a number of 2D. And has there been approach based on machine learning approach where you start from a lot of example where you have the 3D object and you have the camera's view, and you have many examples. They form a database, and from there you try to learn the inverse map. I mean, this is quite quite popular, this type of approach now. I wonder if they have been used in this for this kind of problem, and if it makes any sense.
My guess is definitely it's been done or being done. I don't really, as I said, I don't have a lot of knowledge of the practical side of what's happening in the real world, but I'm pretty sure this is very much on the table, if not already done. So again, if you have some, I guess depends on how much time you have to do these reconstructions, right? So if you have to reconstruct very, very quickly, then probably you want to do something quick and dirty. There are polynomial systems being solved. In fact, some of the fastest ways to solve these systems are based in things like Grosvenor basis and so on, surprisingly. But there's a lot of work that's behind these systems, and some of these polynomial system solvers are running on your phones and so on. Like, but I'm very sure machine learning is used. I can't point you to anything specific.
Thank you very much. No more questions. Don't be shy. But if not, I will thank again Rekha for her lecture.
Just a second, there was a question in the chat.
Oh, there was a question in the chat, sorry. Yes, yes, thank you very much. So we have a question from the chat, which is, what is the degree of freedom for reconstruction? How many pairs of camera will work?
Can you ask the question, Irina, one more time? I'm not sure I quite understand what you're asking.
Maybe you can give the mic to Irina.
Yeah, thank you very much for a very nice talk. So if you know that you can reconstruct a camera, it's probably not unique. There is a certain dimension for the pairs of center, or maybe there is a finitely many cameras, or maybe there is a certain, so you know that you have a configuration when you can reconstruct two cameras.
Right.
What is the variety traced by their centers? Is that what?
That's a good question. So there are some degrees of freedom, because what we're really solving for is the intersection of this determinantal surface with the plane, right? So the surface is degree 3. So when you cut it, depends on the dimension of the plane that we're cutting it with. But typically, for example, one classic case people look at a lot is determinantal surface, and you're cutting it with a plane that is just a line. Okay, so in that case, there will be 3 possible solutions. Now, whether those solutions are real or rank 2 or so on is not easy to determine upfront. So the real and the rank 2 is actually quite a bit more sophisticated than just the complex story. And if you're cutting it with lower dimensional planes, then you can have even possibly infinitely many solutions. But you're interested in cases that are real and rank 2. Does that make sense?
Yeah, yes, thank you very much.
Okay. There is another question by Teresa Crick. Okay, she has a mic. Teresa, you can speak.
Hi, Rekha. Thanks for your nice talk, really. I have a question. When you showed the case k = 4 and you showed the non-chiral configurations,
yeah,
these were always degenerate configurations.
That's
at least
right.
one of
Well,
the cameras.
On one side.
On one side. But
well,
in practice,
not necessarily both sides, right? Like look at E, this
side.
one.
Yeah, but in practice, you will be noisy. So you will never fall on these configurations somehow.
That's right. That's right. So this entire talk and the question that I'm asking is for exact reconstruction. Okay, so I have points, and these let's assume these are exact points, and we'd like to know if there is a chiral reconstruction. If the points were noisy, then we wouldn't try to reconstruct. We would just try to minimize the distance to the set of all possible reconstructions. Does that make sense, Teresa?
Okay. Yeah, yes.
Yeah, so this is the exact geometric question that I'm asking here.
Thank you very much. Yeah.
Okay, thank you very much. So if there are no more questions, we will switch to the next lecture. While Danylo arranges his slide, I want to say a few words on the special meaning of this lecture. We started this cycle of lecture with the winner of the Smale Prize, Afonso Bandera. And we end this cycle with the winner of the Popov Prize, 2020 Popov Prize. Let me say something about the Popov Prize. The Popov Prize was established in memory of Professor Vasil Popov from Bulgaria, who was a prominent leader in approximation theory. And the eligibility for the prize is restricted to young mathematicians removed less than 6 years from their PhD. So this prize recognizes distinguished research accomplishment in approximation theory and related area of mathematics. Danylo Radchenko holds the instructor position at ETH Zurich. He received his PhD in 2016 from University of Bonn under the supervision of Don Zagier. And he was awarded the 9th Vasil Popov Prize on June 5, 2020. He was recognized for a very outstanding contribution to approximation theory, especially theory of spherical design. He has settled together with Bondarenko and Vyazovska a very long-standing conjecture by Korevar and Meyer on optimal asymptotic bound for spherical T design, and also proved with other authors the optimality of the Leech lattice among all 24-dimensional sphere packing. He has also, in earlier work, contributed to the theory of shape-preserving approximation. And more recently, this will be probably more the topic of his lecture, non-uniform sampling theory in relation with Fourier analysis. So we have a fascinating combination of work, intertwined work between approximation theory, harmonic analysis, number theory, and this is going to be reflected in his lecture on Fourier interpolation formulas and uniqueness pairs. Danylo, the floor is yours.
Thank you very much for this very nice introduction. It's a great honor for me to give this talk. I really wished it was a real live talk, but well, that's the best we can manage. So I want, maybe first I want to apologize if I tried to make the talk as untechnical as possible, but I'm kind of, I have a feeling that I might have failed in certain parts. So if you feel like the talk is too technical, either completely or in parts, then, well, sorry, I failed, but I tried. So, and I'll try to make it, I tried to make it not technical at all, but we'll see. So I want to talk about a certain problem in Fourier analysis and harmonic analysis, which really arose from the recent breakthrough work of Marina Wiazowska on the sphere packing problem. And the problem itself is kind of interesting. It appears to be very natural, and as certain special cases, it includes various results, mostly well-known, some lesser-known results in harmonic analysis. And so I will describe this problem. And roughly speaking, the problem is as follows. It's kind of similar in a sense to the problem of the previous talk, except it's more infinite dimensional. So the problem is given a function and its Fourier transform. Of course, we are given complete set of data. We know everything. But let's say we're giving only some partial information. So we're given only some values of function and some values of the Fourier transform. And then the question is, when can we reconstruct everything from that data? And as I've said, there are certain classical results which can be reformulated in this form. And there are certain very recent results which, for some strange reason, involve a lot of number theory, and they are connected to the sphere breaking problem and its generalization, the energy minimization problem. So I will try to explain all that, and then after I explain the connections to this discrete geometrical problem, I will also talk about some progress on the question itself and some recent open problems and conjectures related to that. Okay, so that's roughly the plan of what I'm going to talk about. And the problem itself, the questions that I mentioned just now, is something that I call the reconstruction problem for the Fourier transform. So it's very simple to state. So just to make everything completely precise, I'll tell you what the normalization I use for Fourier transform, which differs among the various branches of mathematics and physics. So I use the normalization in which the Fourier transform is a unitary operator. And I put the 2 pi I into the exponent of the character. So with this definition, the question is, I mean, with any other definition, the question would be the same, but for certain reasons, this one's better because of the connections to number theory. The question is, given two closed subsets of the real line, let's say we're given a function from a nice function space, which I won't specify now because it makes it more flexible and more interesting. And we're given the restrictions of this function to the two closed subsets. So when can we recover the full function from these restrictions? And of course, I mean, there's an obvious answer. If the two sets are everything, then we already know. If one of the sets is empty and the other is everything, we also can kind of reconstruct everything. So I want to avoid the boring answers to this question. So really, we want A and B both to be non-empty and not the full real line. And whenever this reconstruction is possible, whenever there's a unique solution, I'm not saying anything about whether for any specification of these restrictions there is a solution. I'm just talking about uniqueness. So it might not exist, but if it's always unique, then we'll call this pair of sets a Fourier uniqueness pair, or just uniqueness pair. Okay, so and the interesting property, I mean, the point of the kind of interest for this notion is to make the two sets as small as possible. So we don't want any redundant information. And for that, we call this pair, any uniqueness pair, tight if for any closed subset of A and B, the uniqueness property goes away. So if we cannot shrink the two sets any longer, then, or remove points if they're discrete, then we will call them we will call such a pair tight. And another kind of interesting thing, which we don't require for the question itself, but it's actually kind of, it's always useful, both for practical applications and surprisingly for theoretical. So if we have an explicit formula that allows us to reconstruct a function from this data, which may or may not be very explicit, may or may not be known to exist, but for a certain special situation, and I will mention at least 3 different special situations in this talk, such formulas actually exist. And surprisingly, the formulas themselves sometimes exist before we even know the uniqueness result. And they allow us to derive the uniqueness. And somehow the uniqueness is more difficult to derive without explicit formulas. So I mean, at the moment, you shouldn't think too much into that, because I'll give precise examples. And of course, I mean, there's no reason to restrict ourselves to one-dimensional Fourier transform. It doesn't even need to be an abelian Fourier transform. But I will mostly concentrate on the one-dimensional case, except in some examples that follow now. Okay, so now I want to give some examples to maybe give a better idea of what I'm talking about. So there are some very classical results which one can formulate in this form, well, possibly by stretching the definitions a little bit. So the first example is if we consider a tempered distribution on the real line, such that its Fourier transform is supported in one point. So we could imagine that this is, we're talking about the case where the set B is it's not closed, so it doesn't quite fit in the definition I said, but it's just a complement to the 0 in the real line. And then some classical results from theory of tempered distributions tell us that actually f is a polynomial. So whenever we pick A to be an infinite set, a polynomial cannot have infinitely many zeros unless it's identically 0. So from this we get more or less for free from known results that this pair of any infinite set and the complement to 0 is a uniqueness pair. It's not a very good example because it's actually, it contradicts the requirements I put on the sets. So I said they should both be closed. So there is a related result, which is actually an honest example. So if we now look, instead of the Fourier transform on the real line, we look at the Fourier series. So we're looking at functions on the unit circle, and we're looking at the Fourier transform, which is now a function on the integers or the coefficients of the Fourier series. And now we take the set B to be the complement of some discrete interval in the integers, which I take to be centered around 0, but it doesn't have to be. And so the condition, so for the uniqueness property, when the function's Fourier transform vanishes in the set B, which is a complement to a finite set, it just means that the function itself is a trigonometric polynomial of degree at most n. And so a trigonometric polynomial, again, doesn't have too many zeros. It has at most 2n zeros. So as soon as we get the 2n plus 1 points in our set A, we can always reconstruct any trigonometric polynomial from the values. And that means if we also allow, give us the information about the missing Fourier modes, we can also reconstruct any function from the values and on the set A for the function and from the set B for the Fourier transform. So these are kind of not very exciting examples, perhaps. So a somewhat more interesting example, and the one which is well known to people working in time frequency analysis. So the so-called Whittaker-Shannon interpolation formula, or sometimes also called Kotelnikov-Whittaker-Shannon interpolation formula. So I will give a formulation which is not strictly the formula itself first, but it will be easy to derive it from what I'm saying. So as before, now we're talking about the Fourier transform on the real line. So let's say A is the complement of the interval between -1/2 and 1/2. Again, it's like in the previous example, it doesn't need to be centered around 0, but it's convenient for the proof of this statement that I'll give in a moment. And we set the set B to be just the integers. And then my claim is that this pair is a tight uniqueness pair for the Fourier transform. And I'm kind of being a bit sloppy again. I won't tell you which function space exactly we're talking about, but let's imagine sufficiently nice functions. And the proof of the claim is a one-line corollary of the Poisson summation formula. So if you write the Poisson summation formula in this somewhat unconventional way, so usually you would put the sum over all translates over integers on the left, and then you rewrite it as a sum, as a trigonometric sum involving the values of the Fourier transform on the right. So I put everything except the value of f at the point x on the right, and then leave the value at the point x on the left. So if you look at this for a moment, you see that all the values on the right were already given as long as x is in this interval that's removed from the line, as long as x is between -0.5 and 0.5. These numbers are already given by definition because we know the values of the Fourier transform at b. And the values here are also known because when x is between -0.5 and 0.5, x plus a non-zero integer falls outside this interval. So these values were also given. And from this, one can actually get what is usually called the Whittaker-Shannon formula. So let's just assume that the values of the function outside the interval from -0.5 to 0.5 are 0. And then take the Fourier transform of this formula. So then if you actually do this, you will get this identity, which is what people usually call the Whittaker-Shannon interpolation formula. And what it tells you is if you're, except, okay, I mean, I'm reconstructing the values of the Fourier transform, but it's not that different. So it tells you that as long as the support of the function is in this interval from -0.5 to 0.5, actually to know what the values of the Fourier transform are, or the function itself for that matter, it's sufficient to know what the values of the Fourier transform are for integers. And this is an explicit formula that tells you how to reconstruct everything else. So then there's another example, which is somewhat recent in a sense. And this is perhaps the only example where the answer to the question about uniqueness pairs can be given completely. So the setup is now we're talking about a discrete Fourier transform, and we're looking at cyclic groups of prime order. So in this situation, I'm just repeating I'm putting the definition of the Fourier transform. It's not super important. You can imagine what it is. So in this setting, actually, there's a result by Terence Tao from 2005. So he was interested in so-called uncertainty principles, but as I'll explain in a moment, this can be reformulated in the setup that I'm using very easily. So Tao has proved that for any function on the cyclic group of prime order, the sets of the support of the function and the Fourier transform cannot be small at the same time. So there are other known results of this type, but for the groups of prime order, this is the optimal, the best result you can hope for. So it's telling you that as long as you have at least p zeros among the values of f and the Fourier transform, the function has to vanish actually. So you always have at least p plus 1 non-zero values for non-zero functions. And here this S just denotes the support, but I kind of said it already. So what's equivalent way to say it is actually if you say which values on the function side and the Fourier side vanish, I mean, it tells you precisely which sizes of the two sets are allowed. So as a corollary of this result, you get for free that whenever you have two sets whose sizes add up to p, one on the Fourier side and one on the function side, then you get a tight uniqueness pair. And actually, if you think about the dimensions of the spaces you're working with, it's all finite dimensional spaces. The set of functions has dimension p, and actually just by dimension count, you see that this is tight. Okay, so now the result that kind of the more interesting kind of result that has its roots in the sphere packing problem, although directly it's not related to that. So this is something that we proved with Marina Wiazowska about 4 years ago. And the result concerns concerns with a situation where we're talking about the real line, and in the Whittaker-Shannon formula, we had one of the sets was very big and the other was just discrete subset integers. And it's kind of interesting whether one can make both sets discrete. And the example we had is exactly of this type. So if you take all real numbers whose square is a non-negative integer, take this to be your set A, and then you take the set B, you take the same set as before, and then remove 0 from it. So this is a tight uniqueness pair for even functions. You can ignore for the moment this remark about even. I mean, it's almost true for all functions, but there's a slight difference. And I just don't want to go into technicalities that much. So what happens, there is an explicit interpolation formula, which explicit in the sense that all terms appearing in it are explicit. It's not necessarily easy to do all these computations explicitly, but it is everything is explicit. And so it's a linear interpolation formula that allows you to recover all the values of the function from just the values at the square roots of integers and from the values of the Fourier transform at square roots of integers. And well, I'm saying something about sets A and B. So B doesn't have 0 in the example I'm talking about. In the formula, there's summation from 0 to infinity on both sides. But actually, if you remember what the Poisson summation formula tells you, the value at 0 can be removed, the value of the Fourier transform or the function itself. So this indeed tells you that the set A and B, the pair A and B forms a uniqueness pair. What this doesn't quite tell you is why is it tight? And the tightness follows somehow from the properties of the functions an and an hat that appear in this formula. So we actually, so not only they're explicit, we can actually prove a lot of things about them. And one of the properties that we can establish is that the values, if you restrict yourself to the set of square roots of integers, then these functions behave like delta functions. Okay, and then it's not a very difficult exercise to show that this implies tightness, because if you remove any point from the two sets that you have, then one of these functions, an or an hat, would actually be a counterexample. So this problem, I want to spend a little bit of time talking about where this kind of theorem came from. So it came as a toy example of something we really needed for a problem in discrete geometry. And so I want to spend several slides talking about this problem. And I'll try, maybe it will give some motivation to why this formula looks the way it is. So a configuration for me is just a discrete closed subset of d-dimensional Euclidean space. And let's say we're given some kind of energy functional, which roughly you can think about this as a physical setup where the points of the configuration are some particles, and there is certain repelling law which governs the movement of these particles. And this repelling law comes with its potential function, which only depends on the distance between points. And so roughly we're talking about the sum of all interactions between these points, and we want to if we're interested in ground states of the system, we're talking about minimization of that energy. So this is all kind of roughly. I mean, even the definition here is not quite correct, but let's just, I mean, it's correct for finite sets, but it's not quite correct for infinite sets. But for the moment, I just want to formulate the problem. So the problem is, how can we find the ground states of P energy on the d-dimensional Euclidean space? And so in other words, it just means we want to minimize the functional, this P energy functional, EP of C, over all configurations with fixed density. And the density is important, but kind of, I'll explain it in a moment. And then if we can find the minima, we also want to find all configurations which achieve the same value. So usually this problem is too hard. It's very rarely you can solve it exactly. And it's related to certain difficult problems in material science. So it's related to the so-called crystallization problem, which roughly kind of asks for an explanation or for a reason why particles at low temperatures tend to arrange periodically. And it's not quite strictly the same problem, so the crystallization problem is a lot more difficult. There are certain things which one doesn't account for in this simple model, but they're morally related, and both are certainly very difficult. So just to make sure that everything is at least somewhat rigorous, I just want to give these definitions on the slide. So I put quotation marks on the previous slide when I defined energy. There is a rigorous way of defining it. It's given by certain upper limit of certain approximations to the full configuration. It's not too exciting, so I just gave it here in case you're interested in what the rigorous definition is. And the density is just the, again, here's the definition, but morally it's the average number of points per unit volume in the space. So whether it's well defined or not, it's not terribly important. All the problems I'm talking about are perfectly interesting for periodic configurations for which all these limits will exist. Okay, so then there's something kind of mysterious about this problem. And this goes to a paper by Kohn and Kummer from 2003, where they studied the property that they called universal optimality. So sometimes it happens that certain configurations are not only optimal for a single potential, but actually for a very huge class of potentials. And well, there's a certain question about which potentials are actually important. And it's not a very trivial question to answer, but for some reason, most of the interesting potentials have the property that they're completely monotone. And actually, one can relax this a little bit and require them only to be completely monotone functions of squared distance. So it's a small exercise to show that this is a relaxation. And to give some examples, so the most examples that people are interested in are either the so-called Riesz potentials, so just the inverse power law potentials, or the so-called Gaussian potentials, which are just Gaussians in the distance. And there's, in principle, this complete class, I mean, the set of such functions is a convex cone, and the set of Gaussians spans this convex cone, which is a famous result of Bernstein. I mean, it's not terribly important for what I'm talking, but it's useful to know. So what is the mysterious thing about this problem? Well, Kohn and Kummer, based on certain numerical calculations, they have discovered a very strange phenomenon that, so I will describe kind of the reasoning which led them to this phenomenon in a moment, but the basic phenomenon is in certain special dimensions, there are configurations that are much, much better than you would expect. And seemingly this set of dimensions is either finite, the set of such configurations is very small. So what they found is in dimensions 1, 2, 8, and 24, there are certain configurations, well, namely the integer, they're all lattices. So one of them is the integer lattice, one of them is a hexagonal lattice, the E8 lattice, and the Lich lattice. So all these configurations, they seem to be universally optimal. That was their observation. And in fact, it's not quite what they conjectured. They conjectured something much more precise. So they actually gave a recipe for proving this, which is, in general, it seems to be intractably hard to do. But their recipe was much it's much better and much more mysterious, because there's no good explanation for why their recipe would actually work in these dimensions, but it does. So, and what they could prove, usually in one dimension, these problems are very easy. The problem about universal optimality for the integer lattice in one dimension turns out to be, it's not trivial. It's not terribly hard, but it requires some work. So unlike the sphere packing problem in one dimension, for example, is completely trivial. And even in 2 dimensions, it's not terribly terribly hard. So here already in one dimension, there's some difficulty. And I won't say much about any other dimensions in this talk except 8 and 24. But basically, there's, as far as I can tell, there's only one other example where people even expect this phenomenon to happen, and that's in dimension 4. But for a different reason, it doesn't fit into the conjecture of Kohn and Kummer. So this universal optimality property is nice. So I kind of alluded to the connection to the sphere packing problem. What happens is, in fact, the universal optimality is it implies also sphere packing optimality. So it means that if you want to arrange spheres at points on your configuration space, all of them with equal radii, then the best configuration to use, in the sense that you will occupy the largest fraction of the space, is actually the configuration, one of the universally optimal configurations. It's not the case that all optimal sphere packings should be universally optimal. It's not true in dimension 3, but in dimensions 1, 2, and 8, and 24, people expect this to be the case, and also in dimension 4, I guess. So yeah, the only reason I'm mentioning the sphere packing problem is because if you look at this list, 1 to 8, 24, if you forget the first 2 dimensions, 8 and 24 are exactly the dimensions where the sphere packing problem was recently solved. And this is not a coincidence, so it's based on the same principle. So the 2-dimensional case is kind of interesting. I want to say a few words about it, but not too much. So it's still open for the optimality, for the universal optimality problem, so it's open, in fact, for any single potential which is completely monotone. So either you pick whatever value of S you like, pick any Riesz potential or any Gaussian potential with a fixed value of the parameter. If you can prove that A2 is optimal for that, that would be a great breakthrough. So what is known, and that's pretty much state of the art. I mean, it's not a complete state of the art, but it's a good approximation. So it's known, everything is known for lattices. So if you only look at lattice configurations, then it is known that the hexagonal lattice or the A2 lattice is optimal, both for Riesz potentials. So this is a sequence of papers by Rankin, Cassels, Dianand, and Enola from 1960s. And then there is a complementary result by Montgomery that A2 is optimal for all Gaussian potentials, again, among lattices. So if you restrict your configuration space to very small, nice manifold, which describes all lattices, then you can actually solve this optimization problem. But in general, it's very hard. And the methods that are used for lattices are not, don't help for general configurations. So one thing I wanted to show is that one can actually give physical evidence for this conjecture in the shape of so-called Abrikosov lattices, which is another difficult conjecture, which is, you could view it as a physical conjecture or as a mathematical conjecture. It has a rigorous formulation. It's quite different from the universal optimality, but it does follow from it. And one can actually verify this conjecture experimentally. So the conjecture says something about superconductors of type 2 in magnetic field. Namely, there are certain so-called Abrikosov vortices, which appear when you put the superconductor into the magnetic field. And under certain conditions, these vortices tend to arrange in an energetically minimal way. And Abrikosov conjectured that they will always form a lattice. And that's what they do. And you can actually see this with your own eyes. Although I guess this is not quite a microscope picture in the usual sense. It's an electronic microscope. So you can't actually see the wave, the light waves from this picture. Okay, so so let me just explain now how this connects, how this story connects to the one I started with. So I started with something about Fourier transform. Now I was talking about energy and certain discrete sets of points. So the connecting theorem, or kind of an idea, is linear programming. So there's a way, roughly the idea is to replace your complicated moduli space, which is moduli space of all point configurations in Euclidean space, which is terrible, terrible object, very hard to reason with, and replaces with something which is linear or at least convex. And so what you do is you do this relaxation, and in a way, I won't kind of make it precise in the talk, but I'm just trying to explain what this theorem is based on. So the theorem it allows you to give bounds for the energy by not doing any geometry at all, but instead by solving a certain optimization problem for functions. So what you do is, well, you take your potential function, which we assume, I mean, we don't assume much about it. So this works basically for arbitrary functions. They don't even need to be continuous. And so what we want is we want some auxiliary function which will help us obtain certain bounds. And that auxiliary function, which is now sometimes called the magic function in certain cases. So it needs to lie below the graph, the plot of the function, the potential function itself. And it needs to be positive definite in the sense of Fourier transform. So its Fourier transform needs to be positive, non-negative. So whenever you have such a function, which, I mean, one can trivially produce functions which give boring estimates, but there are actually always also functions which produce non-trivial estimates. So whenever you have a function satisfying these two conditions, you get a bound for the energy of any configuration with fixed density rho. For the talk, you can always imagine that the density is 1. I mean, it's a matter of rescaling everything. So whenever you have such a function, you can get a bound. And what's nice is I'm not giving a proof, which I usually do. And the proof is actually very simple. It's basically half a page. And it tells you precisely when the equality is achieved. And so so I'm eating the proof, the equality is achieved precisely when, and I'm kind of simplifying the assumption a little bit. So let's say the configuration we're looking at is a lattice, which is the case for dimensions 8 and 24. We want to prove that certain lattice is universally optimal. So if the configuration is a lattice, then the equality in this bound for the linear, in the bound from the previous slide is achieved if and only if. So these are just the conditions of the theorem. And the only things we need to do to add to that is that the function is equal to the value of the potential. So not just below that, but it's actually equal to at all points of the lattice. And the Fourier transform is 0. So it has to be non-negative, but if we require it to vanish at all points of the dual lattice. So if these two sets of conditions hold, then we automatically get a proof that the configuration is optimal. It's optimal for P. But of course, if we can solve it for all potentials P, then we get universal optimality. So this is the strategy that Kohn and Kummer have suggested. And there's a similar strategy that was done before by Kohn and Elkies, which is the basis of Marina's proof of the sphere packing problem in dimension 8 and our joint work in dimension 24. So, but this is slightly more general. I mean, it's a lot more general and also quite a bit more complicated to do it for all potentials. I mean, so now I'm almost at the point where you'll get some idea as to why the interpolation formula I started with has something to do with this. So let's look at the E8 lattice in 8 dimensions. So it is an even and self-dual lattice, which means that the dual lattice is a lattice itself, and all the squares of vector lengths of the lattice are even integers. So if you look at the conditions from the corollary on the previous slide, let's assume also that the auxiliary function that we're looking at is radial. There's really, I mean, it doesn't weaken any assumptions because one can always symmetrize over all rotations. But let's just assume that it's radial for simplicity. So then the conditions that we have for the function, well, we have the conditions that it lies below the potential, and it actually equals the potential at certain points. Well, if you think about it, it means that it actually is equal to, at these points, to the potential to the second order. So also the derivatives should agree. Otherwise, it would go either above or below the potential, above the potential at some point close to that. And so this means that these two conditions uniquely determine the values of the potential auxiliary function, of the putative auxiliary function at the points square roots of even integers. So it determines the values and the first derivative of these points. And completely the same argument tells you that you also know what the values and the first derivatives of the Fourier transform are at the same set of points. So basically the question becomes, can we recover the function from these values? And it's kind of a very strange thing, which for the longest time, so Kohn and Kummer, Kohn and Elkis knew about this problem, but no one kind of guessed that actually this set of data is enough to recover the function itself. So there's nothing additional you need to assume. And this is what we proved in 2019. So in dimensions 8 and 24, there is exactly the type of formula that you want for the universal optimality. So there is a formula that tells you exactly what the auxiliary function should be. It's quite complicated to actually work out it explicitly, but all the terms appearing here are explicit, and they have something to do with modular forms. And I will not say much about that, but there's a certain connection with modular forms. It goes quite deep, and the formula itself, it kind of can be interpreted in terms in terms of theory of automorphic forms. But for the moment, I mean, there's certainly no time to talk about that. And based on this result, so this result tells you if there is an auxiliary function, then it actually can only be one thing. And it more or less tells you this. I mean, you have to compute these infinite sums in a good way, but it will give you a formula for the auxiliary function as long as you substitute good potential in here. And using that, we actually managed to prove the inequalities. So we managed to establish the conditions from this corollary here. And that gives the universal optimality of the E8 lattice and Illich lattice, which gives also gives a different proof of their sphere packing optimality. Okay. So now I made a long detour into discrete geometry. So I want to go back to the theorem I started with. So there's this interpolation formula, which is roughly similar to what we've seen before. So this one was motivated by the problem about universal optimality. I mean, one has to apply certain heuristic kind of relaxations to this to guess that, well, if we are given values of the first, of the value of the function and its first derivative at slightly sparser sequence, namely square root of 2n, well, what happens if we have a denser sequence, like twice as dense, a sequence that is twice as dense, but we're only given the first, the values of the function, not the first derivative. So this is roughly what happens, and this theorem here, we're stating it for one-dimensional case. There's basically, if you look at the proof of this result, there's an easy way to generalize it to radial functions in d dimensions. So this is why I'm saying this was a toy problem for the result that we actually needed. But it's kind of interesting in itself. So, I mean, one can try to play around with it and try to see if there's an easier proof, well, not of the formula itself, but of the uniqueness pair that it produces. And so far as I can tell, there is no proof which doesn't rely on somehow the arithmetic nature of the set. And so all the proofs I know are somehow also tied together with the modular group acting on the upper half plane. So I'm sorry about mentioning certain words which I won't explain, but yeah, if I were to explain something about the proof, it would take too long. But let's just pretend that, yeah. Okay, so what I want to do now is, first I wanted to show just how these functions look like. So these are the plots of the first three basis functions. So the coefficient basis functions By them, I mean the functions appearing in this formula. And if you look at them, I mean, they do have this property that at the set of square roots of even integer, of positive integers, they do behave like delta functions. So if you look at the functions themselves, so a naught, there's certain normalization factor here, which I wanted to exclude, but let it be. So a naught, it takes value 1 at 0, and it vanishes at all square roots of integers. A1, we don't know about 0, but at positive integers, at 1 it has value 1, and at square roots of all higher integers, it vanishes. And the same thing happens for A2. And then for the Fourier transform, actually all of them vanish at all square roots of positive integers. So, and as you can see, I mean, already the first function looks kind of funny, and the second function has an extra 0. And what happens is, even though we have an explicit formula for all these functions, they're kind of hard to reason with. And for any given n, it's not hard to construct it and to construct a plot, but somehow to reason about them as a function of n is very hard. So just to give you an example of how complicated these functions get, this is just for n equals 50, and this is somehow the Fourier invariant part of the 50th basis function. And the only thing that I should maybe explain is that so here the range goes from 0 to 50. I was talking about function vanishing at square root, taking value 1 at square root of 50. But here I make the change of variable, because otherwise the plot would be a complete mess. So this is how this plot looks like if you take square root of the variable instead of the variable. Okay, and we have, I mean, we have computed some higher plots. They look even more complicated. They seem to be more and more chaotic as you approach 0, but somehow close to the, if you go far enough, so if you go beyond 50, they are decaying very nicely. And I mean, if you want, you can try to check numerically, basically looking at this plot, whether you can see if it's a Fourier eigenfunction or not. It's kind of hard. So I said something about the proof, and what I said was it's very rigid, and it's kind of hard to get rid of the condition that these numbers actually have to be square roots of integers. It's not strictly true. There are some easy things one can do which allow you to do a little bit more general formulas. And one of them is you can shift both sets by a certain number. And so there is a way to do it more or less, again, using theory of modular forms. And for a certain strange reason, this is a precise result. So when a is between 0 and 1/8, these two sets form a uniqueness pair. And if you go beyond 1/8, this is no longer the case. And there is a precise kind of counterexample. So this is still kind of very rigid, because these are still square roots of something in arithmetic progression. There is a nice recent paper by Ramos and Sosa, who've managed to actually perturb the interpolation formula that we have. And as a corollary, they obtain certain perturbed uniqueness pairs of similar type. And I don't recall exactly what the size of the constants they have in the paper. So as long as the perturbation is sufficiently small and it has to decay somewhat quickly to 0, as n goes to infinity. So, and there are no other restrictions. So the perturbations are arbitrary, except that they have to have rapid decay, well, somewhat rapid decay. Whenever that happens, you also get a uniqueness pair. Unfortunately, they don't get, they don't come up with a different proof strategy. They actually show how to perturb the formula that we have for square roots of n. So, which is kind of an issue. So they don't get a new proof of the result for square roots of n, for example. And all of these uniqueness pairs are actually tight. So there's something I want to talk about. Somehow in direction of generalizing these results. And so the question is, can we come up with other examples where both sets are powers of n? And then there's a result by Ramos and Sosa who showed that sometimes it happens, that there is a uniqueness pair. But the more interesting result by Nazarov and Sogin from last May, they resolved everything except tightness. So for all sets of this type, they tell you either it's a uniqueness pair or a non-uniqueness pair, and it's a very simple condition. And even in the something we call a critical case, they basically give a precise description of everything. So, and what's left is something about tightness. So, and somehow their results are very nice and analytic, but first of all, they don't reprove again the result for square root of n. They prove basically everything else. So they have a complete description of uniqueness and non-uniqueness pairs, except for one case, which I form as a question. So specifically for these sets, can we prove that these are uniqueness pairs? And I'm more in favor of them being a uniqueness pair. So I wouldn't put a lot of money on this, but at least for the central case, when alpha and beta are both a half, this is true. Yeah. And another thing is one can generalize the square root case, and then instead of, so we had two examples, one of them with square roots of even integers, another with square roots of integers. So there's kind of a joint generalization of those, where you put a collection of arithmetic progressions instead. And there's a certain density condition, which would give us a critical case. And so I'm conjecturing that whenever you have such a collection of arithmetic progressions, these conditions, that would give you either a uniqueness pair, or it will become a uniqueness pair after extending by finite sets. So why, the only reason I'm mentioning it here is, I've said that we proved the universal optimality in dimensions 8 and 24. In dimension 2, it's a big open problem. And so these types of results should be useful in proving the universal optimality for the A2 lattice. And for certain, again, reasons I can't go into in depth, the modular form techniques don't work for these results. They only work when the number of progressions on both sides is at most 2. And it's kind of a subtle point, but I don't have much time to talk about that. And then we have certain results which are kind of more recent, and in a sense, there were very few tight examples I gave so far, which had these discrete sets of A and B, and basically all of them were about square roots of integers somehow. So there's another example which somehow involves zeros of L functions, in particular zeros of the Riemann zeta function, and logarithms of integers. So again, both sets are discrete. I'm just giving here the interpolation formula that we proved together with Bondarenko and Seip last year. But don't read too much into it. So the only thing I want about this is the corollary, which is the set of zeros of the Riemann zeta function, together with the set of logarithms of positive integers, suitably normalized, forms a uniqueness pair for a certain set of functions, which is reasonably large. And the proof actually gives a large collection of such statements. So it works not only for the Riemann zeta function, but also for some L functions, for zeta functions of quadratic fields, and for Hecke L functions of modular forms. But yeah, this is a bit too technical. So, and probably the last thing I want to mention is the higher dimensional situation. And it is, as one would expect, is more complicated. So there's a very nice generalization of the result of myself and Marina by Martin Stoller from last year. So he basically proves the analog of the square root of n interpolation formula for not just for radial functions, but for arbitrary functions in d dimensions. And so it's a very nice result. However, there's something strange happening for dimensions 2 and higher, where there is these sets no longer are tight. And one can actually remove, so this, if you look at this set, it's just a collection of concentric circles. And if you remove any finite number of these circles, one can still get almost a uniqueness pair. So it's very it's completely not clear what should be the answer. So I'm kind of posing as a question. I'm not sure whether which answer should be more likely. But the question is, can we actually extract just a discrete subset of this uniqueness pair, which would still remain to be uniqueness pair? And it's not clear. So we have some kind of negative results. So certain discrete subsets which look to be very dense are actually not uniqueness pairs, but it's kind of it doesn't clarify which direction the answer to the question should go. So just to show you some pictures, so this is the non-tight uniqueness set that Martin's theorem produces. And this is a non-uniqueness set. So we have a construction which actually gives a set associated to any real quadratic field. And for the quadratic field with square root of 8, you get this set. And if you take the square root of 2021, you get this set. So as you see, they're kind of densely situated in the unit circles. In the circles with radii square root of n. But they're kind of omitting the parts of x's. Okay, so I think I have either very little time or no time at all. So maybe I can either stop here or explain one more thing. No, what would be the best?
Go ahead.
Okay, so there is another conjecture. Yes, okay, good. So there is another conjecture which is actually, I mean, it's, let me just formulate it and then I'll explain why it's important. So if you go back to this linear programming bound of Kohn and Kummer, or Kohn and Elkis, let's just ask the question about what is the best auxiliary function for that problem. And in particular, that would tell us what is the best lower bound for the energy we can obtain using linear programming methods, which in itself would be kind of a big thing because it's not even known what is the best asymptotic linear programming bound for sphere packing in high dimensions. So it's kind of a widely open topic, but there's something kind of interesting which relates to these uniqueness results I was talking about. So if you just solve this problem numerically, which Kohn and Gonsalves did for many different cases, for many values of dimension and many values of parameters, so something strange happens. So actually, it seems like there's always an interpolation formula behind this optimization problem, which is kind of which should be similar to the dimensions 8 and 24, where we actually know this interpolation formula. So here we have some numerical results, and so what seems to be happening is that for dimensions 4 and higher, the above problem has a unique solution, and this solution is actually a nice radial Schwartz function. So the optimizer is a nice radial Schwartz function. And then actually the places where this function matches the upper bound, this like the potential, is a discrete set which behaves more or less like square root of 2n. And the same thing happens for the values where the Fourier transform vanishes. And actually these sets coincide, which is very strange. And we don't really have an explanation for that. And moreover, these sets don't depend on the parameter alpha. So these are kind of some globally unique sets of numbers. And one can compute them to high precision. We don't really see any simple patterns, except that these are asymptotically like square root of 2n. And lastly, there is always an interpolation formula of the type I discussed, the one which we used for the universal optimality problem. There seems to be always an interpolation formula involving these strange numbers. And so for dimensions 8 and 24, this is more or less a theorem, modulo some small thing about whether there are non-radial Schwartz functions. And otherwise completely open, but it's an important problem, I think, because it has potential applications to the asymptotic bounds for sphere packing. So if one had a good understanding of this, one should also be able to do something and probably beat Kobayansky-Levenstein, or at least reprove it. Okay, so maybe I should stop. Thank you.
Thank you very much, Danylo, for this lecture. Please go ahead if you have comments or questions. I have a comment, general comment about this reconstruction formula regarding stability. What type of stability you can expect generally? Is it for the square root of n set? So is it fair to say that you can, if you want to allow some perturbations on the function, on the value, they have to become extremely small at infinity, basically, or it's not a good intuition. What is the noise that you can allow?
Well, okay, so in principle, I mean, we have, so for that, you would need to know how fast these things are growing, right? It's a function of n, I guess.
Yeah.
In principle, you should, as long as your error decays somewhat, it doesn't have to be exponentially, it can be like 1 over n to some power. I think this should be stable. The problem is we cannot actually prove that at the moment. So we have some numerical, so I gave a plot, for example, for the 50th function. Don't remember where, I think it was maybe after that. Right, and here you see it's actually almost everywhere. I mean, here it's just bounded by 1, right, in absolute value everywhere. But we can't even prove that. So our best like estimate for these functions is that they grow like n to the power 1/4. Although on average they are bounded, and actually they're on average they're actually decaying. But it's kind of not clear how much of that can be used to do something, some rigorous error estimates.
Okay, thank you. Other questions or comments? Please go ahead.
Yes, I have one. I would like to ask why, is there an intuitive reason why the interpolation formula starts at 2 for dimension 24 and at 1 for dimension 8?
Yeah, here, yeah. Okay, so there's a reason. Intuitively, it's a little bit harder to explain maybe, but there's a reason why this is the interpolation formula that you want. And it's more or less what I explained here for the dimension 8. It starts at 1 because all the values except 1 don't actually figure in this optimization problem. Sorry, it starts at square root of 2, square root of 4, and so on. The value at 0 doesn't matter. Okay, so for the Leech lattice, in principle, the same thing happens, except the Leech lattice doesn't have square root 2 in it. So it doesn't have vectors of length square root 2. And for that reason, actually, the conditions that you get for the Leech lattice start from 2. And so the theorem that we get is exactly the exact information that we get from this like optimal linear programming bound is exactly what's needed to recover any function. But that's not really an explanation of why it happens. And intuitively, it's a bit harder to explain why this happens. It has something to do with weights of modular forms that are involved. And somehow there's a complementary result which tells you summation formulas of this type, where you include also the values 0 and 1. And the space of those summation formulas we can describe completely. And that more or less tells you where you need to start these interpolation formulas from. Because everything else, I mean, there's some relations between the other values. But unfortunately, like I said, I don't really have a good intuitive explanation for that. So there's like a computational explanation, but it's not intuitive.
All right, thank you.
Other questions? Yes, let's see. Oh, I think that's it. So I want to thank Danylo again and Rekha again for the next lecture, but I also take this opportunity to thank all the speakers for this wonderful cycle of lecture that can all be watched on the YouTube channel. And also thank my co-organizers, Marcus Bachmeier, Agnes Santos, Evelyn Hubert, and Ben Adcock for the help in organizing this. Please, if you want, you can stay. We will now let everyone open his mic and his or her camera, and we can continue the discussion more informally. Thank you again.